is Sarah, and I am going to be presenting part C of the project alongside of Deshawn and Marlon. Alright, so the early lab setup. The first experiments to measure proton mass were done using vacuum tubes and magnetic fields. Scientists used devices like the mass spectrograph, which bent particle paths to separate them by mass. These setups were large and sensitive to outside temperature and pressure changes. Everything had to be aligned by hand and equipment was manually adjusted.
Hello, I am Keyshawn Cantu back with the Proton Mass Project. Continued. For the procedure and equipment use, researchers ionized hydrogen gas to get protons and passed them through magnetic and electric fields. By tracking how much the particles curved, they could estimate the mass of the proton. The setup required careful balancing of fields and measuring devices, all done manually. They had to calibrate the machines often and redo parts of the experiment and if temperatures shifted too much. Data was collected visually using photographic plates and interpreted through extensive manual calculations.
Some diagrams and visuals. Early drawings of these experiments show large coils, vacuum tubes, and curved particle tracks. Equipment often filled entire rooms and needed multiple people to operate. These diagrams help us understand how careful and hands-on early experiments were. And some visual references also highlight how basic the tools were compared to today's standards. Some environmental limitations. Labs didn't have air conditioning or reliable temperature control, which affected the results. Early scientists had to work at night or in colder months to avoid heat-related errors. Even basic tools like accurate light sources or pressure gauges were hard to find or unreliable. Static electricity and moisture in the air would sometimes cause random interference in the data as well.
The equipment and safety issues. Many parts of the experiments involved high voltage and vacuum systems, which were difficult to manage. They often didn't fully understand the materials they were working with, making the experiments risky. There were also no formal safety protocols or emergency response plans. Researchers had no proper safety gear, no gloves, goggles, or radiation protection. Accidents could easily happen due to fragile glassware or exposed wires.
Trouble repeating results and tech limitations. Because there weren't consistent materials or methods, it was hard for other scientists to repeat the experiments. Just the slightest change in equipment or temperature could lead to completely different results. Tools would wear out quickly or behave differently depending on the lab, making standardization almost impossible. And communication between labs was slow, so it took a long time to verify or share findings. Why they pursued it. Scientists were trying to understand atomic structure and needed to know the mass of particles like protons. They hoped this knowledge would help explain how atoms work and why elements behave the way they do. Some researchers believe that unlocking this data could lead to new discoveries in energy or chemistry, and gaining a better grasp of atomic structure was also important for advancing the periodic table.
Who could it help? Physicists and chemists would benefit from more accurate atomic models. The goal was to provide a foundation for future discoveries in medicine, industry, and nuclear science. The work was often funded by universities or national labs eager to be the first to discover something new. Military and defense interests also had an eye on atomic science for its potential applications.
Accidental discoveries. So some of the findings were accidental. Scientists were sometimes looking for something else, like better isotope separation. While working on those, they noticed patterns in the particle motion that helped them identify mass. These accidents turned into major discoveries that shaped our understanding of atomic physics. A few discoveries were so unexpected that they shifted the focus of entire labs. How it was helpful right away. So once proton mass was known, scientists could build better atomic models. It confirmed parts of earlier theories, like Rutherford's model of the atom. It allowed researchers to predict atomic behavior with more confidence, and knowing the proton's mass gave context to earlier measurements of atoms and ions.
The advancements that followed were improved mass measurements made it easier to identify isotopes and sort materials. Early nuclear research, including the discovery of fission, relied on this data. It also helped chemists calculate more accurate molecular weights. Physics textbooks were updated with this foundational measurement, making education more precise.
New areas of research. So this breakthrough led to rapid developments in nuclear energy and particle physics. Universities started creating entire programs around atomic research. Tools like cyclotrons and early particle accelerators were invented to explore more subatomic particles and neutrons in the atomic nucleus overall. Modern laboratory setup. So today we use advanced tools like particle accelerators and mass spectrometers to measure proton mass with extreme accuracy. These labs are kept under tightly controlled conditions, including temperature, humidity, and pressure. Some of the most well-known places doing this work include CERN and labs using penning traps. Scientists use automated systems to make sure the machines stay aligned, and in some labs, robotic arms are even used to help with sample handling.
Equipment and procedure overview. In modern setups, ions are created in a vacuum and sent into special traps that use magnets and electric fields. Computers carefully control everything, how strong the fields are, when they turn on, and where the particles go. Scientists measure tiny frequency changes to figure out the particle's mass. Some systems are smart enough to adjust themselves in real time if anything changes. The sensors are so sensitive that they can detect incredibly small mass differences.
Some modern tools and techniques. So, superconducting magnets and RF signals are used to hold and move the particles. Lasers are used to cool down the particles so they don't move as much, which improves accuracy. The data is recorded and analyzed instantly using advanced sensors and software. And machine learning helps scientists pick out patterns that would be hard to see on their own. Precision technology upgrades. Cryogenics, which means supercooling tools, helps keep instruments stable and sensitive. Some high-powered lasers give scientists more control when working with particles. Some scientists use optical tweezers, which are tiny beams of light, to move particles carefully. New materials like strong alloys are used to build more durable equipment. And nanotech makes it possible to build very small and very precise parts.
Labs now use fume hoods and radiation shields to protect researchers from toxic materials. Automated machines handle most of the dangerous work so humans don't have to. Safety is taken seriously with clear rules and constant monitoring. In high-risk areas, scientists use remote controls to run the equipment from a safe distance. Robotic tools are used to handle radioactive or biohazardous samples.
Data quality and reproducibility. Scientists keep digital records so results can be repeated and double-checked. Labs all over the world work together and compare data. Storing data in the cloud and running simulations helps researchers review and share their work, and open databases make research easier to access for scientists everywhere. So, who benefits today? This research helps scientists work in physics, chemistry, and even medicine. Hospitals use tech based on this research for things like MRI and PET scans. Space and energy researchers use it for developing engines and studying fuel. and environmental scientists use it to track isotope changes linked to climate data.
Scientific and industrial impact. Knowing the proton's mass helps us understand particles and sort isotopes. It supports cancer treatment using radiation therapies. It improves how we test new medicines and chemicals. Engineers use this data to design high-precision tools and materials. It even helps solve mysteries in forensic science.
Related modern research, studies of antimatter rely on very exact proton mass values. Fusion energy research uses this data to test ideas for clean power. Scientists are even using proton data to help redefine measurement standards, and particle mass also plays a role in dark matter experiments. Improving measurement precision. New technology might help reduce the tiny errors in measurements even more. Scientists are working on better ion traps and quantum logic tools. Photonic computing could make analysis faster and more accurate, and better vacuum tech could stop outside interference from messing with results.
Exploring beyond the standard model. Researchers are using proton mass data to look for new particles or forces. This might help us figure out what dark matter is or how the universe works. New experiments could change how we think about basic physics laws. Some believe we might even discover a hidden structure inside protons.
Engineering and tech applications. This knowledge could lead to better energy storage systems. Proton therapy may become more advanced for fighting cancer. Portable mass-based detectors could be used in medicine, the environment, and security, and scientists may create smarter, smaller devices that rely on precision mass data.